Namaste and once again welcome back to online maths class. Last class you have learned Rolle's theorem and we have discussed some examples. And today we move on to exercise 5.8 of Ncert class 12 maths. Let's start. Here the question is, verify Rolle's theorem for the function f of x is equal to x square plus 2x minus 8. X belongs to closed interval minus 4 comma 2. Okay. Before that, let us have a quick review on Rolle's theorem. Rolle's theorem states that f from closed interval ab to r be continuous on closed interval ab, differentiable on open interval ab, such that f of a is equal to f of b. Then there exists some c belongs to open interval ab such that f dash of c is equal to 0. Okay. So first one is continuous on closed interval ab, second condition differentiable on open interval ab, and third one f of a is equal to f of b. If the three conditions are satisfied, then there exists a real number c belongs to open interval a comma b such that f dash of c is equal to 0. Okay. Now here given that f of x is equal to x square plus 2x minus 8. First of all, it is a polynomial function. Polynomial functions are continuous at everywhere. Okay, always continuous functions. So we can write, since f of x is a polynomial, it is continuous. It is continuous on closed interval. Here the interval is minus 4 comma 2. Okay. Now we can find the derivative. F dash of x is equal to 2x plus 2. That means the derivative exists. So we can write f is differentiable on open interval, that particular interval, that is minus 4 comma 2. Now the third one is f of a. F of a is equal to, here a is minus 4. So f of minus 4 which is equal to, we can replace minus 4 the whole square plus 2 into minus 4 then minus 8. Understood? That is 16 minus 8 minus 8 which is equal to 0. And f of b. F of b means f of 2 which is equal to, here 2 square plus 2 into 2 minus 8. That is 4 plus 4 minus 8 and it is 0. Okay, that means f of a is equal to f of b. That is f of a is equal to f of b. That means the first three conditions are satisfied. Then there exists some c in open interval ab such that f dash of c is equal to 0. That c we have to find out. For that we can equate f dash of c to 0. F dash of c is equal to 0 implies, here f dash of x is 2x plus 2. So f dash of c becomes 2c plus 2. Here instead of x I put c. Okay. That is 2c plus 2 which is equal to 0. And 2c is equal to minus 2. C is equal to minus 2 divided by 2 which is equal to minus 1. Clear? Now we have to check whether this number, this minus 1, belongs to the open interval, the given open interval. Given interval is minus 4 comma 2. So clearly it belongs to open interval minus 4 comma 2. Hence Rolle's theorem is verified. Hence Rolle's theorem is verified. Understood? Now we move on to the next question. Examine if Rolle's theorem is applicable to any of the following functions. Can you say something about the converse of Rolle's theorem for these examples? Here three examples are given. We have to check whether Rolle's theorem is applicable or not. Okay. And one more question is there. We have to say something about the converse of Rolle's theorem. Okay. So the first one is f of x is equal to greatest integer x. In class 11, you have learned the function greatest integer function. What is called the greatest integer function? The greatest integer function assumes the value of the greatest integer which is less than or is equal to x. Okay, clearly the function is not continuous. Let's draw the graph of the function. Here the interval is 5 to 9. So I write the numbers from 5 to 9. 5, 6, 7, 8, 9. Here also some 5, 6, 7, 8, 9 and so on. So here the graph look like this. That means from 5 to 5.9999 etc. Okay. The image is 5. But the image of 6 is 6. Okay. That is why we use this symbol. Clear? Then 6 to 6.999. The image is what? 6. But for 7, the value is 7. Okay. And 7 to 7.999 etc. That much value we got it as 7. But for 8, the value come to 8. Okay. So here the graph have so many breaks. So the function is not continuous. Clearly the function is not continuous. So fx is not continuous on closed interval 5, 9. Continuous means without lifting the pen from the paper, we can easily draw the curve. We can draw a smooth curve. Okay. Here it is not possible. Okay. And f of x is not differentiable. Not differentiable on open interval 5, 9. Okay. Understood? Now f of a means f of 5. F of 5 is equal to greatest integer 5 which gives 5. And f of 9, greatest integer 9, the value is 9. Both are unequal, not same. That is f of a not equal to f of b. Here f of 5 not equal to f of 9. Therefore we can say that Rolle's theorem cannot be verified. Okay, here all the three conditions of Rolle's theorem doesn't satisfy. So we can come to the conclusion that Rolle's theorem is not applicable. Not applicable. Now there is one more sub question. Can you say something about the converse of Rolle's theorem? So first of all, we can discuss what's the converse of Rolle's theorem. Rolle's theorem states that a function f from closed interval ab to r be continuous on closed interval ab, then second one differentiable on open interval ab, and third one f of a is equal to f of b. If the three conditions are fulfilled, then there exists some c in open interval ab such that f dash of c is equal to 0. So this is Rolle's theorem. So the converse of Rolle's theorem means let f from a to b to r be a function such that there exists at least one real number c in open interval ab such that f dash of c is equal to 0, then it is continuous on closed interval ab, differentiable on open interval ab, and f of a is equal to f of b. That is the converse of Rolle's theorem. I repeat the statement. Let f from closed interval ab to r be a function such that there exists some real number c in open interval ab such that f dash of c is equal to 0, then the function will be continuous on closed interval a b, differentiable on open interval a b, and f of a is equal to f of b. That means converse means just reverse of the theorem. Okay, understood? So here we have to check whether there is any value of c which satisfies this condition f dash of c is equal to 0. That we have to check. Here we conclude that the function is not differentiable on open interval 5, 9. That means the entire span, the entire interval, the function is not differentiable. If we consider the interval separately, that is open interval 5, 6, open interval 6, 7, open interval 7, 8, open interval 8, 9. In all these intervals, we can say that the function is differentiable. Okay, this span, consider this span, this one. Okay, so in this part, we can say that the function is what? Differentiable. Here we can draw tangents which are parallel to x-axis. Tangent parallel to x-axis means f dash of x is equal to 0. The derivative is 0. Slope of the tangent is 0. Clear? That means dy by dx is 0. That means we can find values of c such that f dash of c is equal to 0. But here f dash of c is equal to 0 doesn't imply that the function is continuous, differentiable, and f of a is equal to f of b, because it is clear that we already proved that f is not continuous, not differentiable, f of a not equal to f of b. So the converse of Rolle's theorem doesn't hold good. Converse of Rolle's theorem doesn't hold good. Understood? So the second sub question, f of x equal to greatest interval, the same function but the interval is different. X belongs to closed interval -2, 2. That you can do it yourself. Okay. Now we move on to the next sub question, and it is f of x is equal to x square minus 1 for x belongs to closed interval 1, 2. Here it is a polynomial. So since f is a polynomial, f is continuous on closed interval 1, 2, and f dash of x is equal to 2x. So f is differentiable on open interval 1, 2. Now f of a, f of 1 which is equal to 1 square minus 1, that is 0, and f of 2, 2 square minus 1, that is 4 minus 1, which is equal to 3. That is f of 1 not equal to f of 2. That is f of a not equal to f of b. So Rolle's theorem is not applicable. Rolle's theorem is not applicable. If all the three conditions are satisfied, then only we have to check the last part. Okay, the given function should be continuous on closed interval AB, differentiable on open interval AB, and f of a is equal to f of b. If the three conditions are fulfilled, then there exists some c in open interval AB such that f dash of c is equal to 0. Okay, here the third condition violate, that is f of a not equal to f of b. Hence Rolle's theorem is not applicable for this function. Now the second part is the converse. Can you say something about the converse of Rolle's theorem? Here f dash of c is equal to 0 implies f dash of x is 2x. So 2c is equal to 0, or c is equal to 0 by 2, which is equal to 0. So we have to check whether the number 0 belongs to open interval 1, 2. No. So 0 doesn't belongs to open interval 1, 2, and hence the converse of Rolle's theorem doesn't hold good. Understood? Now we move on to the third question. If f from closed interval minus 5 to r is a differentiable function and if f dash of x does not vanish anywhere, then prove that f of minus 5 not equal to f of 5. So here it is given f is differentiable. F is differentiable means f must be continuous. All differentiable functions are continuous, but all continuous functions may not be differentiable. Okay, so we can write f is continuous. So here f is differentiable and f is continuous, and let us assume f of a is equal to f of b. Here f of minus 5 is equal to f of 5. Okay, so f is differentiable on open interval minus 5 comma 5 and continuous on closed interval minus 5 comma 5, and we assume that f of minus 5 is equal to f of 5. So by Rolle's theorem we can find some real number c in open interval minus 5 comma 5 such that f dash of c is equal to 0. So by Rolle's theorem we can find some c belongs to open interval minus 5 comma 5 such that f dash of c is equal to 0. But in the question it is given that f dash of x does not vanish anywhere. Does not vanish anywhere means f dash of x not equal to 0. But given f dash of x not equal to 0, this is a contradiction. Therefore our assumption is wrong. Assumption wrong means what is our assumption? F of minus 5 is equal to f of 5. We assume that f of minus 5 is equal to f of 5. That is why we get a contradiction that f dash of c is equal to 0. Okay, so we can conclude f of minus 5 not equal to f of 5. Okay, understood? So that's all for today. This is a very important topic. In this type of questions no need to prove the continuity and differentiability. Normally the questions are based on polynomial functions, logarithmic functions, trigonometric functions and exponential functions. Trigonometric functions, inverse trigonometric function, logarithmic functions, exponential function, that all functions are continuous in their respective domains. So no need to prove the continuity in this type of questions. We can write directly the functions are continuous. Okay, I think you understood the concept. If you have any doubt you can ask me in the comment section. Thanks for watching. Thank you.